Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to continue to talk about the polarity of bonds and molecules. And so in this video we're going to continue with CH3Cl. We ended the last video with NH3 showing that the three polar bonds here lead to you having a polar molecule because the dipole moments, the polarity of the bonds are all pointing in basically the same general direction. And so that means that the overall dipole moment of the molecule also points in that direction. There's no symmetry to cancel out the polarity of the bonds, and so you end up with a polar molecule. And so let's continue with CH3Cl. And if we do that one, let's, where can I write my Lewis dot structure? Let's do it over here. So here I have, I'm going to have carbon and three hydrogens. So carbon, and I have three hydrogens bonded to the carbon. And then I have my Cl chlorine bonded with its three lone pairs. And so there's the Lewis dot structure for my CH3Cl. And so again, you can look at this shape and be able to determine, hopefully, that what the shape of the molecule is. And so here you could see that you've got four bonding pairs, no lone pairs on this. So this would be a tetrahedral molecular geometry as well as tetrahedral electron geometry because we don't have any lone pairs. So the electron group geometry and the molecular geometry are the same. So here you can identify that the polarity of the bonds. Now, here you would have carbon and hydrogen, and you would say, well, there's different atoms, and so therefore there's polarity in the bonds. But if you look at the electronegativity of hydrogen and carbon, they're very, very close. And so the difference between these is less than 0.4, 0.5. I think it's about 0.4. So these are effectively non-polar bonds. So these are not going to have polarity in them. But you can see here in the chlorine, you have the chlorine and the carbon. The chlorine is definitely more electronegative than the carbon to give this a polarity in the bond, to give polarity in the bond. So you're going to have your arrow, your dipole moment arrow, pointing towards the chlorine. That's going to give the chlorine a partial negative charge, and your carbon is going to have a partial positive charge there. And so you have now polarity in this bond. And so since there is no polarity in these bonds, that's going to cancel out the polarity here, then that means that there's going to be an overall polarity in the molecule. So this molecule is polar because you have this one polar bond that's pulling the electrons in towards the chlorine. So the chlorine is, again, pulling that electron density, pulling those electrons in the bond closer to it. So that means you're going to have more electron density over here than over here. And so that gives you the partial negative and partial positive. And so you've got polarity in the bond and therefore polarity in the molecule itself. So what if you have polarity in the bonds but don't have polarity in the molecule? And that's where symmetry comes in. So what you want to notice here is that in this here, here, and here, there is a lack of symmetry in the molecule. So here you've got, this is asymmetrical. You've got two atoms that are bonded together, different atoms bonded together. Here you've got the same atoms bonded together, but notice that they're being pushed down by the lone pair. And so because of that, you have an asymmetry in the molecule, right? So these hydrogens are on this side rather than on this side, okay? And so the polar bonds are all pointing in one direction. Here again, you have a tetrahedral shape, which is symmetrical, right? because so you're going to have the bonds in like a 109.5 degree angle from each other. However, normally that would be tetrahedral and therefore symmetrical, but no, because you have this different atom, it's no longer symmetrical. This side is not like this side. So these hydrogens are different from the chlorine, and so that adds symmetry to the molecule. I'm sorry, asymmetry to the molecule. And so, excuse me. And so that asymmetry is what leads to the overall dipole moment in the bond and in the molecule. So if this was the same atom, like if this was a hydrogen, then all the bonds would be the same, all the polarity in the bonds would be the same. And again, you'd have that symmetry of the tetrahedral molecule, and all of the bonds and all of the polarity in the bonds would cancel each other out because of the symmetry. So we have a good example of that. Carbon tetrachloride. Carbon tetrachloride is an example of a molecule that has symmetry. So let me draw the Lewis dot structure up here. So here I have my 4 chlorines. So I'm going to have a chlorine here, a chlorine there, a chlorine there, and a chlorine here. And if I put my lone pairs on the chlorines, this would be the correct Lewis dot structure. And so here again, using your chart, using Vesper theory, we can know that because we have 4 bonding groups and no lone pairs, this is going to have a tetrahedral shape to it. It's going to have a tetrahedral electron group geometry, and it's going to have a tetrahedral molecular geometry. So because here we have all the atoms bonded to your central atom, they're all going to have the same polarity in the bonds. So again, just like with here, we have the one bond that has the dipole moment, the polarity. So also we're going to have the same thing. So we're going to have an arrow pointing in this direction because the chlorine is pulling on those electrons more. It's more electronegative than the carbon. So you're going to have a partial negative here with a partial positive on the carbon. And again, you're going to have a polarity in this bond with the negative being here. So you're going to have a partial negative there. Did I put that? That should be a negative. So partial, again, for the chlorine on this chlorine here, again, it's going to be pulling on the electrons towards it. So this is going to be a partial negative. And again, in this direction here, you're going to have a partial negative there. So all of the bonds have polarity in this molecule. But because this is a tetrahedral shape, they're all spread out evenly, 109.5 degrees from each other. Therefore, all of these bonds, all of the polarities in the bonds will cancel out. And so therefore, even though we have polarity in the bonds, we're not going to have polarity in the molecule. So the molecule itself will not be polar because of the symmetry. So the symmetry destroys, or quote unquote destroys, the polarity of the molecule. So, they cancel each other out. Okay, so here's an example of a molecule that has polar bonds, but is not polar itself. And so last example would be BF3. BF3 is another example. So if I draw BF3 down here, so if I have boron, this is boron tetrafluoride. And so here is the Lewis dot structure of boron tetrafluoride. You'll notice that boron tetrafluoride is one of those exceptions where boron is happy with less than an octet. And so here we have fluorines. Each fluorine has an octet. And so here, again, from your chart, from Vesper theory, you could look on the chart. Since we know that we have 3 bonding groups, we have 3 total electron groups, no lone pairs. Therefore, the shape of this molecule is going to be trigonal planar. So because this is trigonal planar, we can redraw this a little bit to make it look more like it should be. So we could do this here with the fluorine like that, and maybe move this one over a little bit. Right, so this one would be maybe like that. So this kind of has a trigonal planar look to it now. And so now you can kind of see that because fluorine is more electronegative than boron, it's going to pull the electron density towards it away from the boron, so giving the fluorine a partial negative charge because electrons are negative. And then this one, fluorine is pulling the electrons more towards it, so that's going to be a partial negative. And the same thing with this fluorine too. So this fluorine is also going to be partially negative. So notice that, again, because this is symmetrical, the angles, again, are 120 degrees. So they're equally spread out. And so therefore, the polarity of the bonds are going to cancel out. So the polarity in these bonds will cancel out with that bond, and same with the rest. And so here's another example how you could have polar bonds, but because of the symmetry in the molecule, the symmetry leads to the whole molecule not having polarity, an overall polarity to it. And again, you can kind of look at this as can you divide this molecule in such a way that one side has a positive side and one side is the negative side? There's no way that I could divide this that I'm going to have one side be positive, one side be negative. Same thing for this one. Can I divide this or draw a line through it so that I have one side positive, one side negative? I can't because of the symmetry. Here I can, right? I could draw a line like this, right? I could put my arm there, and it's obvious you have the nitrogen has a negative side to it, and then the hydrogens down here have a positive side. So I can kind of show that has polarity. It has a negative pole and a positive pole. So for these, because of the symmetry, I can't do that. And so this is how you can figure out whether or not your molecule is polar or nonpolar. So I hope this video was helpful. If this clarified things for you, then please help me out. Hit that like button, share it with your friends. Subscribe to my channel, please. Hit that notification bell up there so you can be notified by other videos I put out. Put a comment down in the comment section below. Let me know what you think if you have any questions. Thanks for joining me. Have a great day.